Hey folks, Quilly18 here, and welcome to another episode of our Unity multiplayer tutorial. Now, at this point, we've covered actually all the core mechanics that you need to do your multiplayer game. You know how to sort of register an object to exist on the network. That is to say, you make sure that it's a prefab with a network identity component, and you make sure that after the server instantiates it, the server calls network server.spawn on that object. You know how to send information from a client to the server by running a command, and you know how to send information from the server to a client by running an RPC. There's also what I call a special case of an RPC, which is the sync var. Everything a sync var does, you could implement yourself with an RPC, but it saves you a little bit of timing and typing and is kind of convenient. That's all you need to make a game. Everything else is just, well, what kind of game am I making and exactly how do I use that? Now, in this tutorial, we're not actually making a game by itself, although maybe we could make a game as a future tutorial. If you guys have specific suggestions for what you think might make for a nice, compact multiplayer project that shows off stuff, leave comments down below with suggestions for a game. Maybe it's like, well, let's make a multiplayer version of Pac-Man, or, one of these old classic games. There's, that's something to consider. Anyway, but there's a few concepts that are still definitely worth discussing in the sort of general abstract here, and maybe like go through a few use cases of like, well, how might you do X, Y, and Z for a particular type of game. So I have a lovely graphic over here for one of the core concepts that I think if you kind of use this as kind of a mantra, it leads you to other things that become good, just sort of good general ideas for really any game, but especially when you're multiplayering. And that's the general idea of trying to minimize the amount of network updates. Now, the most obvious problem with being too spammy with how much you send over the network, like running too many commands or running too many RPCs, is you might literally run out of bandwidth, right? Bandwidth is basically the amount of traffic you just jam into your internet pipe. And it can actually, start to fall behind if for some reason you can't keep jamming down enough of that. Now, these days, a lot of people have very fast connections, but not everyone. Not everyone has a lot of upload bandwidth. Downloading is fine, but if you're sending data, either as the server or just a really spammy client, that could get clumped up. And if you're playing with someone, on another continent, then your effective bandwidth is quite a bit smaller. So there's the immediate problem of literally just overloading your network connection. However, that's not really the most typical problem. It's unlikely that you'll probably just run out purely of bandwidth. The most notable problem in multiplayer games is latency, and there's no way to avoid that. Latency is simply the amount of time it takes a packet to go from point A to point B. Now, generally speaking, better networking technologies, which include more bandwidth, tend to also lower latency, but the two are not actually linked that much. A big part of latency simply has to do with how many hops it takes to get from point A to point B, through how many switches and routers and so on and so forth it takes for your packet to get routed over the interwebs. Latency will be dramatically different if you're playing on a local area network versus a remote connection. But even on your own computer, like when we were running the example, we had one client running in the Unity editor and one client running standalone, you still saw a microscopic little delay between the two. And one of the reasons for that microscopic delay that we saw is because by default, Unity's networking is set up to send updates no faster than every 10 milliseconds, because it actually tries to buffer as many packets together and group them up so that if Unity was just sending out the network request the instant that some part of your program was asking for it, I'm snapping my fingers, which isn't very good for audio, but I'm trying to emphasize things, then it would spam out a ton of very tiny packets. Instead, it spends that 10 milliseconds accumulating all these different network requests and tries to cram them into as few packets as possible, which is great efficiency. But that's part of the reason that why even on the same computer there was a slight delay. 10 milliseconds isn't very much, and you wouldn't necessarily notice that. But it still happens. So first of all, I'm not even going to go through a code example. Don't update what hasn't changed. There's no reason to send a network update for something when the value hasn't changed. But that's not something that you often think about. There's a lot of things where we update something every frame, or we run a little function every frame, because the CPU cost for it isn't that great. And honestly, checking to see if something has changed from frame to frame would require a little extra CPU to verify that. It would also require us to save a copy of the old value or keep some sort of dirty bit flagged for if something has changed or not. And if you're talking about on a local computer, it's often worse for you to go through all the work of checking to see if something has changed rather than just, well, we'll do the thing every frame whether or not it has changed or not, because it turns out it's not any extra harder on the CPU overall, and it sure as hell keeps our code a lot simpler. But things are very different in a network setup where there's a lot more it's a lot more overhead. There's a lot more demand to sending something over the network, so it's probably worth checking to see if things have changed. Now, by default, the network transform component keeps track of whether or not the transform has changed, and so it only sends out an update if it needs be. But if you're writing your own version of the network transform, which honestly, I think for many games, you probably will be. I think the only example of, the only example of where you might not bother writing your own equivalent of a network transform is when the things being moved are fairly simple and not terribly critical to things. I don't think you'd actually want to use the built-in network transform component, for example, for your character movement in a first-person shooter, or your character movement if you're doing something like a Street Fighter type game and things like that, because that network transform is written for sort of general use cases, and you might not need it to work exactly the way that it was designed to work. You might need to send less information or more information, or information packaged in a different way or at a different rate in different fashions. So you may end up writing your own version of that is simply more optimized for your particular game. It's not something hard. I mean, the network transform is basically keeps note of your last frame's position, the vector 3. I mean, again, I haven't looked at the code, but one assumes it keeps track of the previous vector 3 position, and if the current position isn't the same as the old position, then it simply sends the vector 3 as a server command, and the server command then turns around and sends an RPC command to all the clients and say, here's the new position of this object. And it would probably do the same thing for rotation, although you can specify which axes you care about and so on and so forth. So you could easily do that yourself. It wouldn't be hard. So that's an example of that. Now, another thing that is another good reason why you'd want to write, say, your own network transform, but that's not the only possible option, is to use prediction when possible. Here's the thing. Then again, there's two reasons to do this. One, if you can have each of your clients kind of predict how your objects move around. It's not the only type of prediction that exists, but if you, for motion as an example, right? If you can have each client sort of figure out where an object's going to move, because you don't just send, say, the position of an object, you also send the velocity of an object, then each client could keep moving that object, that ball, around on its own, because it knows where the thing is going to want to move to, and you don't need to send as many updates. You might still send an update whenever the velocity changes. Now that's a good idea. So now you don't have to send an update whenever the position of an object changes. Instead, you just send an update whenever the velocity changes. Now that update would probably also include the position. So whenever the velocity changes, we send an update with the position and the velocity, and then each client then makes sure that their position is relatively close. And there's a couple of ways to do that. We could actually go and do a little example. So in our player unit over here, let's assume that we've got, so our player unit has a velocity. Now, I could use an actual rigid body to do physics-based stuff with velocities and things like that. Rigid body syncing over a network is a very, very, very hairy topic. Even the built-in network transform has support for rigid body sort of syncing, but man, it's wonky. The best way to do it is maybe have, if you really want something to be a physics-enabled, realistic looking object, you might want to have on the server, have it be a full-on rigid body. So on the server, the full physics of it is being simulated, but on each client, you actually set the rigid body to be kinematic only. So on each client, maybe you don't simulate the physics, but the server keeps updating the clients with the position of the object and so on and so forth. I mean, there's all sorts of different ways of doing it. I'm not going to touch real physics stuff because, man, it is hairy. And again, very game specific. What kind of details can you get away with and which ones are critical for your particular game? Well, then sort of work on that. But let's say, okay, so we have vector 3 with our velocity, okay? And again, this could be a sync var, but let's just do the full RPC implementation because maybe we're going to want to do some other things. Because if you're doing a sync var with a hook, that's the same as an RPC, so we'll just do that and avoid that syntactic magic that goes on. So we've got some sort of velocity, and let's assume, so over here we've got some sort of like if some input, and we'll just put it to true over here so it forces this to run. The player is asking us to change our direction / speed, i.e. velocity, okay? There's some sort of input that the player has given that wants this unit to change its movement. Now, this might be the actual, vertical, horizontal axes for like a first-person shooter type thing, or maybe, again, this could be something like a Zergling in StarCraft, so you don't control that Zergling directly, but you've gone and right-clicked somewhere on the map to issue a move command. The pathfinding AI has figured out which direction it's supposed to go in right now, and so this movement input is actually being fed in from the pathfinding system or something like that. But in either case, in the end, the Zergling is supposed to move in a particular direction, or Duke Nukem is supposed to move in a particular direction for whatever reason that might be. So our velocity has now changed. So what we do on our local client so that we get an instant response is we update the velocity to, whatever new vector 3 it's supposed to be, okay? We'll just, here, 1, 0, 0. It's got some value. It doesn't really matter what it is because it's going to depend on your program. And then what we want to do is we're going to send a command for send updated. Well, I don't know if I want to call it send, because on the server it's going to have the same name. So I guess the command is just update velocity. And we're going to send both the velocity as well as our transform dot position. Now keep in mind, this is being run as the authoritative client, right? We've checked. We has authority over here, over this object. So this is basically the object that is controlled by the local player. Again, it might be controlled by arrow keys, or it might be controlled by a mouse command that translates into some sort of AI command. Or this could also exist if we're on the server and we're actually controlling an AI enemy. Well, then the server is doing this, but it's still doing this sort of update velocity. In fact, the server can call a command. It'll just immediately run on itself, but then you've got one nice centralized area for handling all this. So we have some sort of command that is now called void, and I guess I can copy this, but can I spell things properly? Velocity, boom, like this, and it wants a vector 3 for the velocity, because I have velocity over here. We'll call it V, and vector 3 for position. And here's another interesting idea. Do you have to send a full vector 3? Maybe there's ways to like minimize this, how much information you send. One of the things is if you're talking about a game where you're mostly on a plane, right? You're like a flat surface kind of thing. You don't have to send a full vector 3 for the velocity. You could simply send a single float, which is speed, and another float, which is your rotation through the y-axis. Which direction are you facing and how fast are you going there. So you might be able to minimize the traffic just a scooch that way. I don't know if that's necessarily worth worrying about, but it's a possibility, and for your particular use case, consider that. So this is a command running on the server. I am on a server, and so we're going to want to make sure that the server updates its own data. Okay, so let's have so we've got a command here, but this server is going to want to repeat this command to each client as well. So we're also going to need some sort of RPC, client RPC, void RPC update velocity with the same sort of parameters over here. So I am on a client. And one interesting thing is, if has authority, hey, this is my own object, I should already have the most accurate position slash velocity. Possibly more accurate, for whatever that means, than the server. Because of latency, right? There's going to be a little bit of delay. So depending on your game, right? Depending on the game, I might want to change to match this info from the server, even though that might look a little wonky to the user, right? And it very much depends. Remember, so let's assume there is 100 milliseconds, that's our ping, between us and the server. So it means we've set our position, right? We've done something. We've got a velocity here, and as part of our update, actually, here's an interesting thing, right? Code running right here is running for all versions of this object, even if it's not the authoritative, did I spell that right? Copy. And what do I mean by that is we can go transform dot translate velocity times time dot delta time. What am I doing here? Well, remember, only one computer is the authoritative owner of a particular object. Sometimes that's going to be the server for like an AI enemy. Sometimes it's going to be a particular player. So, you know, my own, or a particular client, for an example of, you know, the own person's player in a first-person shooter, or depending on how it's implemented, they might be considered their own personal authority for, you know, their zerglings in their game or something like that. But this update runs for everyone. And the update, this is something we've done in like a million different copies of every game we've made. During the update, we move our position, right? Transform.translate moves our character, moves this unit based on our velocity times time.delta time. So it's going to move the unit around. And the thing is, even the person who's not the authoritative owner of an object can totally do this. Remember, you can still mess, your code can still mess with an object and move it in any way you want. The thing is, it will not send that information to the network. So you're only doing something on your personal computer. And if you do it wrong, you're going to be out of sync with everyone else on in the game, in the network. And so that might be a bad thing. But this, but even if we're not the owner, we are trying to predict where the object should be right now based on the last velocity update. Or if we are the owner, we've set the velocity from some sort of input over here. So you've got this. Now, whether you want this to be at the top of your update, at the bottom of your update, or, you know, because the whole like nested ifs thing and the fact that we're bailing out of this, the position of this may change depending on exactly how you're working thing. But all of a sudden we have predictive code over here where we're trying to move our object along a velocity that, as far as we know, is correct. So again, let's assume there's 100 milliseconds latency between us and the server. So as a user, this is the object we own. Okay, over here, we own an object, and we've just inputted some sort of like direction change through whatever means possible. So we send a command to the server. 100 milliseconds later, the server gets this information and will want to update, say it's transform dot position is equal to p, and the velocity is equal to v. And then the server now let the clients know the correct position of this object. And so what you do is the server is now telling the clients, hey, we're doing this, and we could just echo v and p, but let's, you know, there might be some sort of verifying of this position, so we'll just send this transformed up, the velocity first. I probably would have put the position first normally, but there we go. So we send this to all of the clients. Now, it takes another 100 milliseconds, and we get this message. Okay, all clients get this message. Technically, it's 200 milliseconds out of date. Now, there are mechanics possible for you to kind of be aware of the latency. Now, latency will change, right? One second, your ping will be 100 milliseconds. A little bit later, it'll only be 50 milliseconds. A little bit later, it'll be 300 milliseconds. The latency and ping times aren't constant. They do change a little bit. So you're going to want to keep track of sort of running average. But it means that we can figure out the correct information. So I'm on a client. If I have authority, I might, depending on the game, actually want to try to make myself move towards the most recent information from the server so we're more or less in sync. This is usually not a critical thing, but that latency compensation is super important. What happens in a first-person shooter? You're moving sideways, right? I'm looking straight forward, and you're moving sideways relative to me. And I shoot where it looks like you are in my game. Well, are you actually there from your point of view? Maybe not, because if you started your move effectively 200 milliseconds before I start your move, where you are on your screen and where you are on my screen are slightly different. So, did I hit you or did I miss you? And this is like a huge aspect of, like, you know, good competitive first-person shooting kind of thing, where you've got this sort of like floating image of a hitbox, and it's, you know, this is well beyond what I can possibly handle here. But being aware of those issues is important. So if we have authority, we might still want to make a change, or we might not. Let's assume for now that we're just going to ignore the message from the server. Okay, so we just return for this. So if we get to this point, I am a non-authoritative, there's no way that's spelled right. Authoritative? Whatever. Client. So I definitely, none of this is spelled right, need to listen to the server. So I'm going to want to listen to the server and do this same sort of thing. We're going to change our position and change our velocity to match. And that means that now we have our, as far as we know, we're as close to possible as the current position of this particular object and its velocity. Although, if we know what our average, or what our current latency is, we could do something like this, where we take our position over here, and we make it equal to P plus V, V times latency, right? If latency is like 0.01 seconds or however it is, then what we do is we don't make our position be where the server just echoed. Remember, this is 200 milliseconds delayed in our example, right? This P position is 200 milliseconds different from the client. So instead of setting our position to there, we set our position actually maybe like times 2. If maybe we have information about the latency between, so we have player 1. Player 1 is the thing that has just moved and has sent this information to the server. And then the server sends this information to us, and we're player 2 at this point, and we're trying to update the position of player 1 on our screen. And we know that, so maybe we do something like our latency plus their latency. So maybe our latency the from the server is 100 milliseconds, but the other person is closer to the server, so the latency is only 50 milliseconds. So now we're adding, we've got 150 milliseconds, or 0.15 seconds, and we're multiplying our speed by that, and we're adding that to our position. And so now the position of player 1 on our screen is as close as possible to what we think his position probably is on his screen right now. And in fact, we probably want to do something similar to that over here, right? So instead, what we're doing is we're setting transform.position. So something like this player's latency to server. So now the server's position is as close as possible to what we think player 1 is on their screen, because we take in consideration. So player 1 sends an update to the server. The server maybe has a general idea about the delay between the two, that player and the server, and so it tries to advance the position along the velocity based on that guess, and then it's sending the player's thing. So now all of a sudden, okay, player 2 no longer needs to know what player 1's latency is, because in theory the position being sent by the server is accurate, it has been advanced and latency compensated. So now we're getting the latency compensated information from the server, and we factor in our own latency and we add that. And in theory, this is as close as possible. Now, the position of player 1 is as close as possible on all players' screens. Given the fact that latency like modifies and it's hard to keep track of and things like that, and that's a whole other science by itself, we, in theory, have synced everything. Now, there's one problem remaining here. And the problem is that we are just teleporting the position. Whether we do this or we do this, we are teleporting player 1's position from where we thought it was before to our best guesses to its accurate position now. And that's probably not going to be very far away, depending on how frequently these updates happen. But if they are pretty far apart, we could be, there could be drift between the two. And, even if it's just, 1 meter, that's, you can tell. We're blinking from one spot to another. Hey, what the hell? So in fact, we don't want to directly update transform dot position, because then players will keep teleporting, blinking as the updates come in. It looks dumb. That's a bad thing. So instead what we want to do is something like this. We want to keep another value, vector3 position, and it's something like this is more like best guess position or something like this. This is where the position we think is most correct for this player. Note, if we are the authority, then this will be exactly the same as transform.position. Because we don't have to guess. We know where we're supposed to be because we're the goddamn authority of this particular object. But for everyone else, we get sort of a best guess position. Now, our best guess position is what we were directly updating. Because P, especially if we do this first, right? Let's say we do it this way. This transform.position, this is our best guess as to what the player's object should be. Our player's position should be. And right now we're directly updating the position, and therefore we get a teleport. But instead what we can do is this. Instead, let's not update transform.position directly. Instead, what we're going to do is update best guess position to be equal to, and we're going to do this. And we'll do something like float our latency. This is a constantly updated value about our latency to the server, i.e. how many seconds it takes for us to send a one-way message. Or receive a one-way message is really sort of our sense here. That's the important part. So somewhere in here, we're going to want to keep track of what our latency is. And really, this is not something you're going to want to track per unit. Instead, this is probably to do. This should probably be something we get from the player connection object. But it's just in here as a dummy value so that technically this code compiles, okay? So now we've got the position we got from the server, which the server has already adjusted for its own latency to player 1, but we're player 2 in this example. plus the velocity of the object, right? Which actually we could move this way, just so that, you know, there we go. The velocity of the object multiplied by our latency, which right now we just have set to 0 because we're not sending it anywhere, but assume that this comes out, you know, our latency is like 0.1 seconds or something. So now we have this best guess position. So now, instead of directly updating the position, what we do is we set the best guess position. This is where we think the player correctly is. And then what we do is over here in our input, we do something like this. Let's say, okay, we aren't the authority for this object, but we still need to update our local position for this object based on our best guess of where it probably is on the owning player's screen. Okay? So now all of a sudden, so let's tell you what, let's go and take this transform over here. If we get to here, we are the authoritative owner of this object. So there you go. We can do a direct translation, and that's fine. But if we're here, what we do is this. We start to update. What is our best guess of this object's position? Well, our best guess of this object's position is the current position plus the velocity times time.delta time. Okay, so our best guess of this object's position is moving based on this velocity. And then what we're going to do, instead of teleporting our position to the best guesses position, we can smoothly lerp to it. So we're always going to be sort of trying to smooth the current position on this player's screen. So we're on player 2's screen. So we're always trying to smoothly move player 1's object. Like, we're player 2, but we can see player 1. We're trying to smoothly move the player 1 object from where it currently is on our screen to where we think it should probably be to best match where it is on player 1's actual screen. So we could, I mean, literally just do something like transform dot position is equal to vector3 dot lerp from our current position to the best guess position and some sort of speed. You could keep some sort of actual value here for time, or you could just I'm a big fan of doing something like time dot delta time multiplied by some sort of float latency smoothing factor 10. So the higher this value, the faster our local position will match the best guess position. So if it's a very high value, then we might get like quasi-teleporting or really fast sliding from one position to another. Now, if the distances are small, you won't notice that. It's still better than actual teleporting, but it's a little fast slide. If the update is fairly far out of whack, then it might look a little funny to slide. But on the other hand, the higher the value, the quicker we get as accurate as possible. If we've tuned it down, then it'll be more slow to update from one position to another, but it'll look super smooth. So we multiply it by some sort of latency smoothing factor like that. So we update our best guess, and then we move our position towards this best guess. And with a high latency smoothing factor, it'll very quickly get to the point where the transformed position and the best guess position will be in the exact same place. Now, there's a lot of different ways to smooth this. So there's like predictive and post-dictive stuff and all kinds of ways to compensate for latency and things. Maybe you want to use a PID controller. There's like, you know, there are probably whole books written about these particular mechanics. But all of a sudden, we have a system where you don't actually have to send this update very often. Now, in some games, the velocity of a player or whatever is going to change constantly, right? Because they're constantly typing in inputs or whatever. But it doesn't have to be the case. The other thing is, on some games, there's actually, you don't even have to send the velocity directly, or you might want to, but let's say we're doing a spaceship kind of game. And instead, in addition to sending the velocity, you are communicating something like the thrust value, which, is some vector 3, plus an angular or turn rate, something, turn rate value. Yeah, it's being very confused because of my, lack of syntax over here, right? So you've got the spaceship sets its thrust and, is turning at 10 degrees per second. And so we could send that as part of the update velocity information. And so now all of a sudden, each client receives the latency adjusted position of this object, the current velocity of this object, as well as the rate of change in velocity, right? This is acceleration. Thrust is acceleration. So velocity, right? Velocity is the rate of change of position. So position is a spot. Velocity is the rate at which that position changes. Acceleration is the rate at which the velocity changes. And the same thing can occur for rotation, right? So we can send a quaternion, or we could send like just a Euler vector for the rotation, which would be fine. Since you're sending a current rotation, you don't have to worry about gimbal locking or anything like that. So we could send the vector 3, the Euler angles of our rotation, but we can also produce the turn rate. The turn rate is basically the velocity for rotation, so the rate of change of the rotation. And maybe there's some other input we can provide which represents the... Because the turn rate, if let's say it's a Newtonian physics system, once something starts spinning and has angular velocity, and assuming there's no drag because we're in space, it'll keep spinning at the same rate. But if you're activating your side thrusters or your RCS, then the turning rate will change because someone's actually either trying to turn faster or they're trying to stop their turning so that they're, just facing in one direction. But we can communicate all that stuff and send all that information as part of the network update. And all of a sudden, each client, in theory, is going to be able to predict with more and more and more accuracy where the other person is, how fast they're going, how fast that movement's going to change, how fast they're rotating, and how fast that rotation is going to change. And you get a surprising degree of prediction available there. So I guess this video has gone fairly long. So that brings us to use prediction when possible. We're going to talk next time about figuring out what is deterministic. Now, that's very similar to prediction, but with some extra caveats. So we'll wait until next time to do that. Thank you very much for watching, folks. Hopefully, again, we're not making a game as is, but if you've got suggestions for a cool, simple multiplayer game that we could do as a tutorial, let me know in the comments. Small scope, again, a multiplayer version of an old classic like Pac-Man or something might be a really, really good way to go, and it would be worth doing. But we have to talk about multiplayer in the abstract here as much as possible, because every multiplayer implementation was going to be fairly different because the kind of information you pass is going to have to be completely different. They all do the same thing. Commands send messages to server, RPCs send messages to client, boom, that's it. But what you send is going to depend very much on your particular use case. Thanks for watching. See you next time. Bye-bye. Thank you to all the January Patreon supporters and these Mic Check supporters at Yukofin, Lurking Ninja, Dubious Sir Curl, Tiburon, Mighty Mix, Pavel Zdanov, Adam Keenan, Michael McClintock, Aaron Doibson, Rarskal, Gurko Dries, Jesper Bisgard, Julien Gelafon, Soren Tried Anderson, Marisfield Vold, Speedy Savant, Steven Stager, Thomas Oberson, Jason Yanity, Easter Egg Productions, Neil Blakey, Milner, and everyone who watched, shared, favorited, and subscribed. Thank you so very much.